That's my point.
Yeah, I was gonna start with this. It's not. Please.
Huh? So you're graphing all three of them on the same, so we're kind of showing how, remember to get this volume function, we had to multiply our height times our area, right? So this is kind of showing us graphically when we have the height and the area, so just my line and parabola, when I dilate those, essentially I'm creating what kind of function? Cubic function, right? So we can see that graphically. We've seen that in the table. Think about how, okay, to get this, when we're multiplying the volume function here for our cylindrical planars, height is what kind of function? Okay, so we're multiplying a linear by base area represents what kind of function? Okay, so we're multiplying a degree 1 times a degree 2 to create a degree 3, which is giving us that cubic. Okay, think about how this is different from, we had rectangle boxes, we are multiplying what kind of factors? Okay, so width was, what kind of function was that? Well, someone help them out there? Think about we were multiplying for the, like length times width times height, I was multiplying 3 things. What would the degree of length and width and height be if I wrote them as functions? Okay, they would be linear, but when I multiply them all together, I'm still creating the cubic function. So now we've seen 2 different ways to create these cubic functions. So on your paper it'll say the 2 cubic functions you've sketched in this lesson represent 2 general shapes. So I went ahead, my bad. So when it's talking about the 2 we've done, this is the first one we did. So this was the graph of the volume for the rectangular planars, right? So it's saying they're different, and then number 4 asks, how can you describe these 2 general shapes? So I'm going to erase, I'm going to just leave up my cubic part of this, maybe, see what it is. So we can compare this cubic to that cubic function. So this was the cubic function when we had to multiply a quadratic times a linear function, and this was when we had 3 linear factors. Okay, so what's different between these 2? What do you mean by, can you explain what you mean by that, Chloe? I see what you're saying, but let's get it out.
Like, linear across the y-axis and linear. I don't know.
So when you said one's vertical, one's horizontal, which one would you say is vertical?
The one we just did.
So this one? So what is this one doing? Huh? Okay, so this function is only increasing across the entire domain. So what are we talking about when we're talking about across the domain? What am I looking at? Okay, I'm looking at from left to right of my x values. I'm constantly increasing. Well, Chloe, what's this function doing? Or what's this cubic function doing? Is it only increasing?
No, it's
Okay.
increasing.
Right, so we have intervals of increase and decrease, and also think about something else you consider when asking these questions is how many x-intercepts do I have over there on that graph?
1.
And how many do I have here? Okay, so we're gonna start talking about when we get into lesson 4, we're gonna kind of start talking about like the multiplicity of zeros and stuff, which we've already visited in the past, but you'll see, remember when we had our 3 linear factors to create the volume function for the rectangular prism, the linear factors, that's where they cross the x-axis at. Do you guys remember doing that? Or do you guys remember that idea? Okay, so keep that in mind. Keep in mind like where our factors cross the x-axis at, and how does that relate to my final function that we're creating? Oh, so for number 4, sorry, you do want to write, when describing these 2 general shapes, that one graph is constantly increasing with one x-intercept and the other is increasing and decreasing with 3 x-intercepts. So just because one's increasing the entire time and the other one's increasing and then decreasing, does that mean the other one's not cubic anymore?
No.
What makes it cubic? The degree, but graphically, how do I know these are both cubic functions? Right, the shape. Okay, so we'll talk about more about x-intercepts, as I was saying, like multiplicity and stuff, like next. It's coming up. So, yes, so remember like these, we can have different characteristics, but that doesn't change the fact that it's a cubic function. Okay. So this is part of your homework that was due today, but when Mr. Kenny looked at what y'all did Friday, something wasn't right about it. We gotta focus on setting up our zeros, identifying the zeros. Did you say this would actually be due tomorrow?
Yeah, so this was, your graphic organizer was supposed to be submitted. Did anyone actually give me the graphic organizer first off? Okay, y'all got 4 terms. I need y'all to do them so that you're reflecting, learning, growing. This was supposed to also be turned in today, this number 1 and the number 2 below it, and there was some practice. It'll be on the slides in a second. Because we're going over this based on the issues we saw, I'll let you submit this tomorrow. Guys, I need y'all to silence your phones in the future. Really quickly, Ms. Courtney's going to cover all the really important things, but Anthony Buchanan came up to me after first block, and the graph for B is very incorrect. So ignore the graph for g of x, do your own function for the dilated function there. I don't know what the book was doing.
Okay, so the main problem we solved, like, remember, so we were practicing dilating functions, like, Friday when you guys were with me and Mr. Kenny wasn't here. And before you can graph, like, your final product, we made a table, right? We made a table, and the first thing you did was you determined the x values that you're going to use to figure out everything else, okay? You know what I'm talking about? Okay, so in doing that, it is very important to identify the zeros. Because remember, our zeros tell us where we're crossing the x-axis at. So when we're creating that new function, that's telling me where I'm going to cross the axis and essentially where I'm creating the curves of that cubic function. Okay, so identifying your zeros first is going to affect what your graph looks like the final product. So, looking at A, f of x is 1/2 x plus 1 times x minus 3. And then but my final product I'm sketching is going to be x plus 1 times f of x. What kind of function am I going to be sketching? Like, what's my final product going to look like? Why do you think it's going to be a parabola? So this is this f of x, this is my parabola. It's showing it already. So, but when I have to multiply x plus 1 times f of x, that would be a cubic function because why, Jaden? Because I'm adding another degree to it with that other x. So, okay, I have a cubic function. How many zeros am I going to have? Okay, well, can you tell me what they're going to be? I haven't done anything yet, but can you tell me what my zeros are going to be?
You have a double zero.
Okay, how do you know I'm going to, okay, let's just start there. How do you know I'm going to have 3? Okay, what's given to you?
The roots.
The roots. Okay, well, if I know one of my zeros, can I figure out all of them using that method? But if I have a cubic function,
You don't need 3.
okay, so let's see what they are. So we did say, well, how did you get the positive 3, Jaden? If it's got an x minus 3 in the parentheses. Okay, so we took the inverse, but guys, don't only take the inverse. Essentially what that inverse is coming from is by setting this linear factor equal to 0. Remember Kenny showed y'all that a few days ago? Okay, so then to get the positive 3, I'm still isolating x, right? And I'm showing you guys this because I don't want you to look at this factor and say my 0 is -1. Because that's a mistake we made in first block. When we need to set this factor equal to 0, so then from here, what's my x-intercept going to be? Okay, so we'll subtract 1. X. And then, how do I isolate x now? Okay, so now I have a 0 at -2. Do I have another 0? What's that one going to be? Okay, so I want you guys to see that my third 0 is going to be x equals -1 because the final thing I'm graphing is the product of this linear factor times this linear factor times this linear factor. That's what it's saying here by this times f of x. Well, f of x contains 2 things. Okay, I can pull out my zeros from that and also from this one, and that's going to help. So then you create your table, right, with those x values, including our zeros, and then counting by like halves or whole numbers, something like that. It's a good general way to go, but make sure you have the zeros on your table because that's where your graph's going to cross, and that determines if it's right or not. Okay, let's go to lesson 4. New lesson. Okay, so now we're going to be decomposing functions. Does anyone need this copy? Okay. Okay, so we have some new learning goals. We're still kind of connecting characteristics and behaviors of these functions back to their factors, building cubic functions from linear and quadratic functions graphically. So kind of exploring more ways to build, or different ways we can build those cubic functions. Determining zeros and multiplicity, which we've briefly kind of covered multiplicity in lesson 2. We're really going to get into it more. Comparing functions and showing how linear, quadratic, and cubic functions demonstrate the fundamental theorem of algebra. Where did I put that now?
No.
Oh, and yeah, so our new word here is multiplicity. Okay, just getting started is a difference in degree. So it's explaining that another name for a linear function is not a constant. Wait, you know that another name for a linear function that is not a constant function is polynomial of degree 1, because the greatest exponent in the linear function equation is 1. Okay, quadratics are polynomials of degree 2, and cubics are polynomial of degree 3. Okay, so our directions for number 1, A through F says determine the degree of each function. So before we do that, do you guys understand all the terms in this like intro part?
I thought poly meant like many, right?
Yeah.
So how does a linear have many if it's just one? How does that have a many degree if it's just one?
So polynomials we use to describe.
Would that not be mon?
So it can also be it would also be a monomial. Well,
Binomial. It's how many
Linear?
terms. Well, I guess A would be a monomial,
so it would be.
and B would be a binomial.
Oh wait, okay. So okay, sorry. So polynomial monomial is talking about the number of terms that are in the. But then the degree determines the type of the type of polynomial, I guess, or type of function. But the polynomial, it's many.
I
We'll
think
get to.
yeah, I think polynomial, it might be best explained as like is the bigger group of functions, and a monomial is like a special type of polynomial that only has one term. Is that it? I'll think about it. We'll try to develop something. to talk
Yeah,
about
we'll get back to
tomorrow.
this one. Sorry, Jaden. But good question, for sure. Okay, so let's get back to this. Yes, we're determining the degree of the function, but then in number 2, it wants you to pay special attention to just C through F, and okay, you're going to identify how many zeros this function has, or sorry, yeah, how many and what they are, and then what's the multiplicity. So, what is multiplicity? Like, look at your book and tell me what it says multiplicity is.
How many
How many
times?
times
There's
are
no
there?
like zero before I do it.
Okay, so if I have, so like, let's look at E here, for example. How many zeros do I have here in E?
2.
What's the degree of this function?
Cubic. 3.
So if I have a cubic function, how many zeros am I have? What are they?
Oh no, you have 3 because you say x equals 0. You just x for 0.
Okay, so one of my zero, so we'll write degree 3. Okay, how many zeros did we say we had? We got 3 zeros, so I have, what's my first 0?
0.
Those are both my zeros. So we have a 0 at 0. What's the multiplicity of that one?
X 0.
How many times do I have a 0 and 0?
1.
Just once. Okay? So I have a 0. So you can say that x equals 0 with a multiplicity of 1. Okay? What's my other 0?
X equals 1 with multiplicity of 2.
Okay, do you guys see where he's getting that from?
Yes.
So, Jesus, why does this one have a multiplicity of 2? Because we have it twice. Okay? So, x equals, not 2. With a multiplicity of 2. Okay. Okay, so in your groups, guys, go ahead and continue, do the rest of them. You don't have to talk about zeros and multiplicities for A and B. Why not? Not only they're simple, why are they so simple, Jane? What's different about those functions, A and B? Those are linear functions that cross the x-axis how many times? Okay, so this is why we're kind of talking about multiplicity for C and F, C through F. So you'll do that, number 2, and also go ahead and start looking at number 3. You're looking for, it just asks you, okay, what do you notice about the degree in the function and the number of zeros it has? Okay, so y'all go ahead and talk about that. And I'm coming around. So right now we're working on that getting started in your groups. Yeah. Yeah, I was just looking over it. You're fine. Yeah, guys. So remember when we're talking about zeros, it's where we're crossing the x-axis at, right? And so our zeros are when x equals that value. Okay, so we want to write it like that.
Yeah. That's over. I forgot my number.
So
But you would have to, you know, say.
You got to put the degree in the
Oh, no, no.
So just put.
say that again. So remember, degree just determines like what it's going to look like on the graph. It determines our function family overall. The degree of the function can change, but then like within that, the zeros and
That's not how I got it.
well,
I know, but I'm saying that
the degrees are based on like. So even if you quadratic, like you were graphing, that's what it would look like. Yeah. Yes. Yes. No. Because what else we got right? What else we gonna ask?
No, this one got 2
Let me
zeros.
go over.
This one got 3 zeros. This one got 1 zero.
Okay, so the degree tells
No, this one
us.
got 0 zeros. This one only have 2. This one only have 2
This
bars.
one will multiply x times x minus 1 times x minus 1. How many linear factors multiply?
Gotta be going 7.
Okay, so it's kind of based off the grid of x's in a sense, but it only those x's are linear. We're gonna talk about that more, but remember, right, because if you, well, also like if you graph that times x times x is x squared, what is that graph?
That's what we looking at.
Okay, guys, let's come back up here. Okay, David, C is what degree? Okay, so guys, remember which I also talked to this about this in first block. So when we're talking about the degree of a function, remember that's what's defining what my function is, telling me what it's going to look like on the graph. Those ideas, right? And then from there we can analyze the zeros. We analyze the zeros within the degree, but the type of function, the shape's still not changing. Okay, so this is going to be degree 2, meaning that it would look like what on the graph? A parabola. And then, Jaquan, what's one of my zeros and number in C? What's a 0?
There we go.
Kelly, can you help me out a little bit? What's a 0 that I have in 3? I mean C, sorry. Okay, so we have x equals 0. with a multiplicity of 1. Okay, well Jaquan, if Caleb told me that I have 1x or 1 0 at 0, hey Jaquan, can you look up here please? Where would my other 0 be at? What number? X equals. Okay, and how many times do I have that?
Why do you keep asking?
Because I want you to learn.
No.
That's so good.
I don't like you called.
It's okay, we all gotta learn. Okay, looking at D. Well, what do you guys notice about D here?
There's a lot going on.
There's a lot going on, but does this look like anything we've worked with before?
Yes.
Factored form of
Quadratic.
quadratic equations, meaning we know this is going to be a degree what?
Two.
Okay, degree 2. So how many zeros do I have?
Two zeros.
Sorry, let me ask, what are my zeros? Or what is my 0?
One.
So we have a 0 and x equals 1 with a multiplicity of. Okay, and then F. Jesus, what are my zeros? Or first, what's the degree of this function?
That's 3.
So how did you know it was a degree 3, Jesus?
I just looked at the X.
You looked at the x's. You notice we were multiplying three linears, right? 3 linear functions. Degree 3. And then, what's a 0, Chloe?
X equals 0 with the multiplicity of 2.
Okay. And Momar, what's the last 0?
1.
With a multiplicity?
1.
Okay, so keep this. And now just look at number 3 and ask, what do you notice about the zeros of the function and then the degree that this function is? Well, we did answer 2.
What are you asking?
Number 3, guys, we did 2. It was asking about the multiplicity and the zeros. We just kind of wrote them all where they belong, okay? Look at number 3. Now it asks, what do you notice about the zeros of the function in relation to the function's degree? You see a relationship there?
Same.
It's the same. Is it the same every time?
Yeah.
Okay, that's the fundamental theorem of algebra. So we're going to write this down because it's not explicit for you where we need it to be. So we're going to write under number 3. That the fundamental Okay, so it states that a degree in polynomial has, including the multiplicity, counted, exactly in zeros. Okay, so go ahead, take a second, write that down, and then we'll talk about it. Yeah, what's up?
Sorry, dumb question, but
No, it's not.
you say like N, are you saying like N, or are you like?
So yeah, okay, that's what I'm gonna talk about. So n is representing a number. So like a degree n polynomial. So I can replace, if I have a degree 2 polynomial, with the multiplicity, I'm gonna have exactly 2 zeros.
Why you know like N?
Yeah.
N is just a,
There.
yeah, but also like when I think it's kind of talking about like when we write like the general form of the equation, like it's just in the place with like the degree. Huh?
It's an interchangeable value.
What do you mean by interchangeable?
You can change it out for any other number.
Yeah, so it's just saying, right, so this would be like our general rule. Like if you look at a polynomial and it's a degree, if I have a degree 5 polynomial, how many zeros am I going to have? Okay, if I have a degree 200 polynomial, how many zeros am I going to have? Okay, but remember that's including the multiplicity, so like here, I had a 0 of 0 twice, right, so I had 2 distinct zeros that were different, but total I had 3 because we're following the fundamental theorem of algebra says if this is a degree 3 polynomial, I have 3 zeros. Okay? So when you're finding zeros with their multiplicities, you want to make sure that all the multiplicities add up to whatever your degree is. Okay, that's what you're going to be kind of looking for. So moving on to 4.1, it kind of introduces us with saying, consider this quadratic function you created to represent the cross-sectional area. So we didn't do this rain gutter thing, but essentially it's still telling us they compose 2 linear factors to, what kind of function would I create if I dilate 2 linear factors? Right, so that's what they're saying they did here, and now we're going to kind of learn, or it's going to show us how we can use our linear factors to sketch the quadratic function without using technology. Like you can just use the features of the graph to do that. So below that you're shown this, and these are the graphs of the equations that's talking about. Y'all see what I'm saying?
Yep.
Or y'all see where I'm looking at? So it graphed our 2 linear functions, and then notice how it divided this coordinate plane up into 3 regions. What did it divide them up based upon? Like how did it know where to split this plane up?
Just trying to find the zeros.
Okay.
One's for 0, the exact one.
Okay, so notice wherever my linear function crossed the x-axis, they drew vertical lines to divide the plane up. Okay, so now we're splitting it into, I have 2 zeros, right, which is going to create 3 regions. So they labeled it Asian region A. I don't even know how I flipped that. Region A, region B, and region C. So then our first thing it tells us to do is label the zeros of each function with open points on the coordinate plane and on the number line below. So notice how this number line down here correlates to, or corresponds to the values that are on the x-axis. Okay, so what you guys are doing here